Good morning and welcome to the session Laplace transform of derivatives and integrals. In this session we are going to recap the Laplace transform, some problems on first shifting theorem, Laplace transform of t raised to n, Laplace transform of derivative, Laplace transform of integral, and finally some practice problems from this session. The definition of Laplace transform says that L of f of t is equal to integral 0 to infinity f of t e raised to minus st dt. And the last session we have learned how to find Laplace transform of sin at. L of sin at is a by s square plus a square. L of cos at is equal to s by s square plus a square. Please note the difference between these two transforms. If sin, then there is a constant in the numerator. If cos, then there is s, the free variable, in the numerator. Then first shifting theorem, L of e raised to at into f of t is equal to f bar of s minus a. Change of scale property says that L of f of at is equal to 1 by a f bar of s by a. Then linearity property, L of a into f of t plus b into g of t is equal to a into f bar of s plus b into g bar of s. That means Laplace transform of scaled sum is equal to scaled sum of individual transforms. For a revision, we will consider the function sin h at, that is the hyperbolic function sin h at. We are going to find Laplace transform of sin h at. To evaluate Laplace transform of sin h at, I rewrite sin h at as e raised to at plus minus e raised to minus at by 2. Then we write the definition of Laplace transform. L of f of t is equal to integral 0 to infinity f of t into e raised to minus st dt. Here f of t is sin h at. Therefore, L of sin h at is equal to integral 0 to infinity sin h at into e raised to minus st. Now replace sin h at by this exponential expression. That is e raised to at minus e raised to minus at by 2 into e raised to minus st inside the integral. Integral is a linear operator, so I can take the constant 1 by 2 outside and split this integral into two parts. That is e raised to at into e raised to minus st is the first integral, minus integral of e raised to minus at into e raised to minus st. Both the integral varies from 0 to infinity. Now integral 0 to infinity e raised to at into e raised to minus st dt is a familiar form. You just think f of t instead of e raised to at. Then integral 0 to infinity f of t e raised to minus st is nothing but Laplace transform f of t. We use this result. And therefore integral 0 to infinity e raised to at e raised to minus st dt is Laplace transform of e raised to at. In a similar way, we can say that integral 0 to infinity e raised to minus at into e raised to minus st is L of e raised to minus at. That is next step. So 1 by 2 into L of e raised to at minus L of e raised to minus at. But we know that Laplace transform of exponential function is equal to 1 by s minus the coefficient of t in the power. So 1 by s minus a. So L of e raised to minus at is 1 by s minus minus a. That is 1 by s plus a. Now we simply cross multiply this expression and simplify. So we got a divided by s square minus a square. Now we just compare Laplace transform of sin h at with Laplace transform of sin at. In the last session we have learned Laplace transform of sin at is a by s square plus a square. Now Laplace transform of sin h at equal to a by s square minus a square. It's only one difference, that is in the place of plus now we have minus in the case of sin h at. Okay. Next problem is find Laplace transform of cos h at. Only difference is the definition of cos h at in terms of exponential functions. Cos h at is equal to e raised to at plus e raised to minus at by 2. First of all, we write the definition of Laplace transform and rewrite cos h at in terms of exponential sum. L of f of t is equal to integral 0 to infinity f of t e raised to minus st dt, and therefore L of cos h at is equal to integral 0 to infinity cos h at into e raised to minus st dt. Now we rewrite cos h at as e raised to at plus e raised to minus at by 2. Then we take this 1 by 2 outside and split the integral into 2. Integral 0 to infinity e raised to at into e raised to minus st dt plus integral 0 to infinity e raised to minus at into e raised to minus st dt. And dt is missing. This expression is simply Laplace transform of e raised to at. This is Laplace transform of e raised to minus at. That is next step. 1 by 2 into L of e raised to at plus L of e raised to minus at. L of e raised to at is 1 by s minus a. Here plus L of e raised to minus at is 1 by s minus this minus a. So 1 by s plus a. Cross multiply this expression, and on simplification we got s by s square minus a square. Here again we compare Laplace transform of cos h at with Laplace transform of cos at. The only difference is in the denominator. The plus is now become minus. That is L of cos h at is equal to s by s square minus a square, but L of cos at is s by s square plus a square. Next problem, that is a theorem related to recursive relation in Laplace transform. This theorem states that L of t raised to n is equal to n by s into Laplace transform of t to the power n minus 1. L of t power n is equal to n by s into L of t power n minus 1. We will prove this using the original definition of Laplace transform. We prove like this: L of f of t is integral 0 to infinity f of t e raised to minus st dt, and therefore L of t raised to n is equal to, instead of f of t we just write t raised to n, integral 0 to infinity t raised to n e raised to minus st dt. Now this integral is a product. We will use integration by parts. First function t raised to n into integral of second function e raised to minus st minus integral of derivative of the first function into integral of second function. So we simplify this. T raised to n into integral of e raised to minus st equal to e raised to minus st by minus s, limit varies from 0 to infinity, minus derivative of t raised to n is n t raised to n minus 1. I take that n outside. Integral of e raised to minus st is e raised to minus st by minus s. Here also integration is with respect to t, so we take this minus s outside. And we put limit in the first term. When we put upper limit infinity, e raised to minus st becomes 0. Minus, when we put lower limit, here is a t raised to n, so 0 raised to n becomes 0. So upper limit is also 0, lower limit is also 0. 0 minus 0, 0. Then minus into this minus gives plus. In the numerator we have n, denominator s. So n by s, integral 0 to infinity t raised to minus n, t raised to n minus 1 into e raised to minus st dt. Now we compare this integral with our Laplace transform. Here we multiply t raised to n minus 1 by e raised to minus st, then we take integration. This is nothing but Laplace transform of t raised to n minus 1. N by s into Laplace transform of t raised to n minus 1. So we start with LHS in the first step and RHS in the last step. That is Laplace transform of t raised to n is equal to n by s into L of t raised to n minus 1. Again we can apply the same result for L of t raised to n minus 1. In that case we get the power n minus 1 by s into L of t n minus 2, like that. N minus 1 by s into L of t n minus 2. Again we apply Laplace transform of on t raised to n minus 2. So we get n minus 2 by s into L of t raised to n minus 3. We repeat like this. So we got an expression like n by s into n minus 1 by s into n minus 2 by s into etc. Then L of t is 1 by s into L of 0. L of 1. L of 1 is equal to 1 by s. When we use L of 1 is equal to 1 by s here, numerator becomes 1 into 2 into 3 into etc. n, that is n factorial. Denominator becomes s raised to n into s, that is s raised to n plus 1. We start with L of t raised to n in the left side. L of t raised to n is equal to n factorial divided by s raised to n plus 1. Now we are going to formulate a definition for L of t raised to n. One thing we have to keep in mind that to apply this 1 into 2 into etc. n as n factorial, n should be a positive integer. But it need not be true in all the cases. And therefore we generalize the definition like this: L of t raised to n is equal to n factorial divided by s raised to n plus 1 if n is a positive integer. And if it is not a positive integer, that means a fraction or some negative numbers, anything other than positive number, in that case this n factorial will become gamma of n plus 1. Actually gamma of n plus 1 is generalization of n factorial. Gamma of n plus 1 is actually generalization of factorial. Now we define what is gamma of n. Gamma of n is a special function defined as integral 0 to infinity e to the power minus x into x to the power n minus 1 dx. There are some useful results related to gamma function. Gamma of n plus 1 is n factorial when n is a positive integer. That is, here if n is a positive integer, this gamma of n plus 1 automatically become n factorial. So we got the first result in this condition. And again gamma of 1 by 2 is equal to root pi. Gamma half equal to root pi. And again gamma of n plus 1 is equal to n gamma n. This is another recursive relation. Gamma of n plus 1 is equal to n into gamma of n. Now we move on to a key idea of this session, that is Laplace transform of differentiation and integration. What happened when we take Laplace transform of derivative? Suppose a function f of t is defined in time domain and its derivative is denoted by f dash of t in time domain. When we take the transform, in the transform domain it automatically becomes a product with s. The Laplace transform will be multiplied by a power of s. That's all. So in a simple words we can say that the Laplace transform transforms differentiation into multiplication by s. That is a theorem. The transform of the first and second order derivatives of f of t satisfies these results. That is L of derivative of f of t of first order, that is equal to s into transform of this f of t minus f of 0. This f of 0 will be a constant because it is an initial value given to f. So ultimately this will be the result. We multiply transform by s. So differential operator will disappear. In the case of second order derivative, L of f double dash of t is equal to s square. Here we have second derivative, so s square into L of f of t minus s into f of 0 minus f dash of 0. Again f of 0 is a constant, f dash of 0 is another constant. They are actually initial values. In that sense, second order derivative is transformed into multiplication by s square. Here also we have an s term. There are some mild conditions. One is this f dash and f double dash are piecewise continuous. Then only we can apply Laplace transform. And also the function f of t on this right side should satisfy the boundedness of growth conditions in existence theorem. If we generalize this Laplace transform of derivative of nth order, we got Laplace transform of nth order derivative is equal to s to the power n f bar of s minus s to the power n minus 1 f of 0 minus s to the power n minus 2 f dash of 0 minus s to the power n minus 3 f double dash of 0 minus etc. minus s into f n minus 2 of 0 minus f n minus first derivative at the point 0. So when we take Laplace transform of nth derivative, the right side contains a polynomial expression which contains powers of s raised to n, s raised to n minus 1 etc. Or simply the differentiation operation in time domain is transformed into an algebraic operation in transform domain. That is the advantage of using Laplace transform over derivatives. We will use this result in the case of solution of ordinary differential equations. Solution of ordinary differential equation need not be simple in the case of higher order differentials or with the varying type of functions on the right hand side expression. That is in the non-homogeneous case. But the Laplace transform will help us in that area. When we take the Laplace transform, automatically the differentiation become an algebraic operation in S. Then we simplify the algebraic expression. Then we take the inverse Laplace transform. We get the original solution. That is the use of Laplace transform in solution of ODE. The second idea is Laplace transform of integral. We know that integration is the reverse process of differentiation. We expect the same thing in the Laplace transform also. If we take the Laplace transform of derivative, it is transformed into multiplication by s. Then we think like this: if Laplace transform the reverse operation of differentiation, then we get the reverse operation in the transform domain. Or in simple words, Laplace transform of integral is equal to division by s. We simply divide the Laplace transform by s. We try this guess in this theorem. Let f bar of s denotes the transform of the function f of t, which is piecewise continuous for t greater than or equal to 0 and satisfies the growth restriction. That is in the existence theorem of Laplace transform. Then for positive s and for s greater than k and positive t, Laplace transform of this integral becomes f bar of s by s. Yes, the guess is true. If we take Laplace transform of integral, this is simply dividing the transform by s. There is no additional terms with the right hand side. In that sense, if Laplace transform of double integral f of tau d tau gives f bar of s by s square, or generally Laplace transform of n integral, nth integral, n times integral becomes f bar of s by s square. So operation becomes very simple. We simply divide f bar of s by powers of s depending on number of integrals on the left hand side. Now we revise Laplace transform of general functions, not in single expressions like sin t, cos t like that. Here I take sin square 2t. We know sin square 2t is sin 2t the whole square. That is sin 2t into sin 2t. We know Laplace transform is an integral of a function f of t and e raised to minus st. There is also a product. If this f of t is again a product, we have to integrate three terms. There is no direct result to calculate integral of product with three terms. It may be complicated. In such situations, we can use some reduction approach. We know sin square theta is equal to 1 minus cos 2 theta by 2. And so, Laplace transform of sin square 2t is equal to Laplace transform of sin square 2t can be written as 1 minus cos 4t by 2. Now this is simply a difference, linear expression. So I take 1 by 2 outside, apply linearity property, L of 1 minus L of cos 4t. Then we use the result for L of 1. L of 1 is equal to 1 by s. And L of cos 4t is equal to s by s square plus 16. Now we can simplify this using cross multiplication. So s square plus 16 minus s square by s into s square plus 16. S square minus s square becomes 0, so numerator becomes 16. Then 16 by 2 is equal to 8 in the numerator. So we got 8 by s into s square plus 16. That is Laplace transform of sin square 2t is equal to 8 by s into s square plus 16. Here note that we are not applying the original definition of Laplace transform. Instead of that, I use Laplace transform of 1 and Laplace transform of cos 4t. They are basic results. Another problem is find Laplace transform of sin t into cos 2t. Again the same scenario. Sin t into cos 2t is a product. If you are using the sin t into cos 2t in the original definition of Laplace transform, it is simply integration of a product with 3 times. Instead of that, I convert sin t into cos 2t as a sum using our sum formula. We know that 2 sin a cos b equal to sin a plus b plus sin a minus b. Here there is no 2, so I take a 1 by 2 here. Then t plus 2t, 3t, sin 3t plus sin of t minus 2t. T minus 2t is minus t. Sin of minus t is minus sin t. That is why this minus here. I directly use this result. Apply L on both sides. Laplace transform on both sides. L of sin t cos 2t is equal to, we apply linearity property. So 1 by 2 outside. L of first term, L of sin 3t minus Laplace transform second term, Laplace transform sin t. Laplace transform sin 3t is 3 by s square plus 3 square. that is 3 by s square plus 9. This minus is here. Laplace transform of sin t, here coefficient is 1, so 1 divided by s square plus 1 square. Again cross multiply this expression, and note that we simplify only the numerator, we never expand the denominator. So we got 1 by 2 into 2s square minus 6 divided by s square plus 9 into s square plus 1. I can take a 2 common outside. That 2 and the 2 in the denominator will get cancelled. So answer is s square minus 3 divided by s square plus 9 into s square plus 1. Next problem is find the Laplace transform of cos root t. There is a natural tendency to use the direct formula for Laplace transform of cos at, but it cannot be used here because here there is a root on t, and therefore we simply use the power series expansion of cos t. Power series expansion of cos t is equal to 1 minus t square by 2 factorial plus t raised to 4 by 4 factorial minus t raised to 6 by 6 factorial plus etc. plus some t. This stands for an even term, t raised to n by n factorial, or more generally t raised to 2n by 2n factorial. It is more correct. Then what is Laplace transform of cos of root t? Here in the place of t we have root t. So root t square is t, root t raised to 4 is t square, root t raised to 6 is t cube, because we take on 6 by 2, 4 by 2 like that in the power. And here also we assume 2n, so 2n by 2 is n. Now it is okay. Here we have to choose t raised to 2n by 2n factorial, that is correct. Then this is a sum. So apply Laplace transform on both sides. L of cos root t is equal to L of 1 minus t by 2 factorial plus t square by 4 factorial minus etc. Now L of 1 is equal to 1 by s. L of t by 2 factorial. First you take 1 by 2 factorial outside. Then L of t raised to 1. L of t raised to n is n factorial by s raised to n plus 1. Here n is 1. So 1 factorial divided by s raised to this 1 plus 1. So 1 factorial by s square. Similarly, here I take 1 by 4 factorial outside. L of t square is 2 factorial divided by s raised to 2 plus 1, that is s cube plus etc. Now we generalize this infinite series as a sum. Sigma n equal to 0 to infinity. Here alternate terms are plus minus etc. So there is a minus 1 raised to n in the term. N factorial divided by, here we have even number factorial. So 2n factorial into s raised to n plus 1. 2n factorial into s raised to n plus 1. One thing we have to note is this is not a closed form expression because it contains infinitely many terms on the right side. It is not like Laplace transform of cos at is equal to s by s square plus a square. It is not like that fixed answer. That is a problem with when t is like a power fractional power root t or third root of t, like that. In that case, the right side need not be a closed form expression. So it's a special case. Next problem is Laplace transform of cos of at plus b. Again we apply cos a plus b result because this b is a constant. We need cos of at, sin of at, like that. So split it into two terms. Cos a plus b is equal to cos a cos b minus sin a sin b. So Laplace transform of cos at plus b is equal to Laplace transform of cos a cos b, that is cos at cos b minus sin at sin b. Now apply linearity property. Cos b is a constant, take it outside. Cos b into L of cos at minus sin b into L of sin at. L of cos at is s by s square plus a square minus sin b into L of sin at is a by s square plus a square. Now the denominator is same, so we can combine the numerator in a single denominator. So s into cos b minus a into sin b by s square plus a square. Here also we apply a trigonometric relationship, cos a plus b equal to cos a cos b minus sin a sin b. It's an identity. So this is all about in this session. Here we simply revisit the Laplace transform definition, some of its popular properties, and we revisit some problems in order to come into the track. Then we learn how to find Laplace transform of n to the power of t, then Laplace transform of derivative and the Laplace transform of integral, and we will practice some problems in the next session. Okay, thank you very much.